Welcome at our event 615 million for quantum. Proposed, approved, action. Quantum Amsterdam is the innovation hub for companies to explore and develop quantum software, technology, and new applications. Our mission is to connect academia, industry, and society by facilitating knowledge exchanges and innovation. Therefore, we organize meetup events, workshops for companies to learn more about the possibilities of quantum technology, and our knowledge partners such as Qsoft, CWI, University of Amsterdam, Amsterdam University of Applied Sciences, AMOF, and Surfsara have already set up collaboration projects with the industry. If you are interested and want to learn more, please visit our website www.quantum.amsterdam or contact our Quantum Innovation Officer Koen Groenland. And for now, please enjoy the rest of the afternoon with our big meetup event. Yes, welcome everybody. Good of you to be here. We are very excited to bring to you this first big meetup event organized by Quantum Amsterdam. You might be here because you've heard that Quantum Delta NL has been awarded 615 million euros to boost the development of quantum technology in the Netherlands. And today we're going to talk with 4 distinguished expert speakers, scientists also, that will tell you what they will do with part of this money, but also 2 speakers from abroad who will inspire you in what they would do with this amount of money. And since we weren't sure that Quantum Delta NL would have awarded this grand amount of money, we first didn't invite the last speaker, or actually the first speaker. And now it's a special guest. It's the co-director of Quantum Delta NL and founder Jesse Robbers. And he will talk about what the national agenda for quantum technology actually means. Well, my name is Yvonne Smit, and I'm your host for today. I'm the coordinator, communication and impact at Qsoft, but I'm not alone today because I have a co-host, and here he is, Dimitri van Esch. Dimitri, how are you?
I'm good, thanks.
Can you tell a bit about yourself?
Yeah, sure. So I'm Dimitri van Esch, quantum lead at ABN AMRO and a solution architect. I created the quantum program in 2018 at ABN AMRO, still managing 2 quantum projects, came in touch with Qsoft and QTech, and in that sense, also connected to Quantum Amsterdam and organizing these kind of things. So I'm really looking forward to this.
Yes, I'm very glad that you're my co-host for today. And before we start with Jesse's presentation, I have a couple of announcements. There's a video director backstage. His name is Koen Groenland. You already met him in the movie. And if you have any technical difficulties, please address your questions to him. There's Koen. Hello, Koen. And if you have questions to the speakers, then there is Martin Tijdsma, who is the education officer at Quantum Amsterdam and lecturer at the Amsterdam University of Applied Sciences, and he will bring your question to us so we can ask them to our speakers. Now, you can type your question on the right-hand side here in Slido, and Martin will make sure they come to us. You can do that during every presentation, but there's also time at the end of this first part to interact with our scientists and our speakers. So let's continue with our first speaker. As I mentioned, his name is Jesse Robbers, co-director and founder of Quantum Delta NL and senior business consultant at TNO. Jesse, the floor is yours.
So thank you much. Thank you very much for the introduction, and thank you for the invitation to present what we have done until now from the Quantum Delta perspective. So hopefully that we have jointly a great event this afternoon. And I'm gonna start with the assumption that you all know that what quantum technology is, what qubits are, and that the articles that I put here in the slides are not quantum technology at the moment. So that's my assumption. So I'm not gonna explain the technology there. I'm gonna explain the roadmap and the developments that we have done with quantum delta. And of course, I think the majority of the people that are have joined today are aware of all the quantum developments that are going on, and the front page news that was last month, maybe last 2 years, couple of years, there about quantum technology and the breakthroughs that were there on different technologies, different areas, and different countries in the world. And with Quantum Delta, it started in autumn 2019. We started to build up the national agenda of quantum technology, where we gave a perspective of what's happening in the Dutch market around quantum technology, what's happening on global scale, and what needs to be done to accelerate this development and this technology from a Dutch perspective and from the Dutch institutes. It was received by the State Secretary Mona Keizer, and it was well received, and it was later on awarded, and I forgot now the time there, with a start impulse of 23 million to boost up the program and build up the program and start some first activities, where I come later on. The program was built and the national agenda was built with the key stakeholders in the Dutch quantum technology field, from leading institutes like QSoft, QTech, QTE, the University of Twente, Leiden, and TNO, who were the main stakeholders in the development of the national agenda quantum technology, but also were the main developers of the proposal for the awarded Groeifonds recently. The program was built up on three main pillars to accelerate in that pillar or that vertical or that domain, the developments. So focusing on the development around quantum computing and simulation, focusing on the development and deployment of quantum networks, focusing on the setup of applications in the quantum sensing area, and is supporting with a couple of action lines to do some long-term and applied research and innovation, an action line to build up the ecosystem, build up startups, support startups, and accelerate spin-outs of the institutes that are working on quantum technology, translate the developments of quantum technology to educational topics. Educational topics on not only how you call it in Dutch academical level, but also on HBO and MBO level, the people that you need to have in your environment to build machines, to build hardware, to build software code that are coming from a lower level of education. Maybe it's not that the right word, but the people that are working not on the academical level there, and an action line on the social dialogue. What is happening and what is the impact of quantum technology on society, and what are sort of ethical discussions that we need to start up with the development of quantum technology. And not to forget, also the nano community is connected to the quantum delta environment to boost the national clean room infrastructure there, the nano labs that are also necessary to build up the quantum technology elements, hardware for our future developments there. So I said three main catalyst programs to focus on the development of applications and demo versions in the quantum computing area, to make openings for business, government, students to get some experience with the quantum computing technology, and do collaboration with the different players in the ecosystem, hardware, software, institutes, industry, institute, university, etc. And the second one is about national and to build up a national network. So the main goal that we have in this domain is to build up a national network in 5 to 7 years from now, to connect the different areas where quantum technology is developed, to exchange, of course, in the end, qubits, get a stable network there, to run applications on that network and connected to that network, but also to build use cases and test beds in relation to, for instance, mobile network, cloud solutions, and security applications. And the third pillar about sensing applications, there's already some hardware available there, but how can we use this? How can we build up this? And how can we build software around it to use these sensing applications? And luckily, later in the program, Florian's track is giving more information about what's happening in this area. And as said, the action lines of the CATs are supported by the 4 action lines to focus on breakthrough, to develop breakthrough technologies, do more research and innovations in the complete field of quantum technology. So not only focused on the pillars around quantum computing, quantum networks, and sensing, but also to appealing technologies to the quantum field. Build up the ecosystem. We really built up and started already with a pre-seed fund to start to boost the ecosystem around startups. Yesterday also there was an announcement of the collaborations that has started there with the funding, the pre-seed funding from the activities from Quantum Delta with QFox in the Lightspeed program. And as said earlier, the programs around human capital and the dialogue around the impact of quantum technology on our social life and ethics. Then in autumn, we built up and translated the national agenda into the Quantum Delta entity that was founded on September 23rd at the City Hall of Delft with the Mayor of Delft. And there the program started to executing with the starting pulse that we have received. So we have started the activities from that moment in the field of quantum computing and quantum networking, and to build up the ecosystem in action line 2. And we started to build up further the Groeifonds proposal that we have sent earlier this year. Quantum Delta is focusing to play a central role there, to connect the pioneering in the technology, to focus on breakthrough applications and technologies, to connect and to centralize the developments around international high research from the Netherlands and in cooperation with other developments internationally. And important also for the Netherlands and the national government is to accelerate the possibility to get funding, to get I forgot the word, verdienvermogen, to accelerate the industry around this, to create jobs, to create revenue, to create new possibilities with this technology for the Netherlands and with the Netherlands in Europe. We have done that not only with the institutes, as I've presented earlier. We have done this with many players from the industry, recognizable players from a bank, from the banks, from telecom operators. Luckily also that Dimitri and Jaya are here, as they are connected to ABN and KPN. But there were many players involved in this, and many players also supported the proposal that we have done there. We have received more than 90 support letters from the industry on our proposal for the Groeifonds that is awarded now. Also, the startup area is very important for us because we see in the ecosystems in Amsterdam, Delft, but also in Eindhoven and Twente that many spin-outs, startups are there already and more to come. And we will try to push this further. And also their support and their collaboration is crucial in the success of Quantum Delta and the quantum ecosystem in the Netherlands. And then a couple of weeks ago, I think nearly a month ago, we were awarded with on our proposal. We have built the proposal as a summary of the national agenda. We did a request for a certain amount of money, and we were awarded in the innovation vertical of the Groeifonds with the full amount that we have requested, which is a great result of the work that is done with many players in this field. And also, I think it never happened that so much money was allocated once in a proposal, and also once in a proposal that is about the future and not about the history, like we're also investing in trains and etc. Then what are we going to do with it? So if you look into, for instance, the CAT programs, we start to expand the ecosystem around the quantum computer that we have and that we have built up around the Quantum Inspire platform. Focusing, of course, to work with more qubits in the quantum computers, focusing on the spin qubits and the supergeleider qubits on a short term. Hopefully that we can expand it quickly also with the Rydberg qubits, and then focus on these three, and in the next phase, after 3 years, evaluate if we are successful there or not, or that we need to shift in that area. And then build up the ecosystem around it with the new technology players, with new technology that is founded there and what is developed there, and that we can spin out also to new technology, new propositions, new possibilities there. Quantum Inspire, as launched in 2019, in cooperation also technology-wise with the supercomputer from SURF, Cartesius, is key there, and focusing on tests, simulations, applications with the field is really important there if it comes to the CAT1 program there. Then if you look into the CAT2 program, we are focusing on, and we have started already there with expanding the R&D networks that we have in the Delft area, in the Eindhoven area, where we do some research and test on short notice to develop hardware and software to come to a national network there, what we call the national staging network that we're going to deploy in 5 to 7 years from now. That should be a sort of stable network there where we can build applications and connect other applications to the network there, and then transfer the technology also in supporting the industry startups with using the networks and the experience into building, for instance, their own networks on national level, on local level, but maybe also on EU level there. So the main goal in the CAT2 program is that national network between the different locations. And this is an idea of how that network could look like. The yellow part already are in development and deployment there. The blue one is the goal that we want to set up there, but it could be also in the development upcoming period that this picture will change a little bit because of the learnings that we have. Then if it comes to the quantum sensing part, the focus will be on the application development with the hardware that is there, develop a couple of test beds there to do some tests and to work further on the improvement of these sensors and hardware around it, and do some first-time engineering and industrialization. Again, Florian Schreck is also in this session and can tell more about it. Important also is to understand that the proposal that we have done there is awarded there. So it's the fund that is allocated there is allocated and is awarded to the plan that we have delivered there, and which is a subset of the national agenda quantum technology there. So we don't start from scratch. And the plan is much bigger. We are talking about now about the 650 million, but the overall plan is bigger. Funding from Europe, funding from the industry in real money, but also in kind, is important and crucial for the success of the program there. And there a couple of things already are set in the plans to execute the upcoming period, but there are a lot of open possibilities, like in Action Line 1, but also in the CAT3 program, where there are possibilities for calls to add technology, to get funding for doing research, but also in the Action Line 2 program, there are funding mechanisms to boost the startup ecosystem and the developments around it. And in the end, we have the goal to build off the Silicon Valley of the quantum, with more scientists, with more graduates, with more PhDs, with more companies in the field of quantum technology in the Netherlands and more direct jobs in this field, because that's the goal what we would like to achieve as an ecosystem in the Netherlands. And in my opinion, it's important also for the Netherlands. The Netherlands is always driving on digital infrastructure. We are one of the key players in the digital infrastructure in Europe. The digital infrastructure in Europe is mainly positions around the FLAP locations, Frankfurt, London, Amsterdam, and Paris. Quantum computers will be the fundament for the high-performance computers, the hyperscalers, and the cloud area. Digital infrastructure and quantum networks are the next generation of quantum networks and quantum internet that is necessary there, and the applications, like also the focuses of QSEF, is important to use the future infrastructure there, the quantum computers and the quantum networks there. So I hope that I gave you a brief view what's happening on Quantum Delta, what the overall plan is, what we're going to do with the award of the funding, and where we have started already. So if you have any questions, let me know, and let's jointly kick some qubits and make it a success in the Netherlands.
Yes.
Yvonne, are there any questions?
For your great presentation. There's at least one question from the audience, which is saying the European Quantum Industry Consortium fosters the common interests of the European quantum industry. How will Quantum Delta NL interact with them?
A couple of two of the institutes became member of the QUIC consortium on European level, and currently we starting also the discussion with the stakeholders in the Netherlands. How can we collaborate there? How can we bring value from Quantum Delta to the participants in QUIC and the other way around? But that needs to sort out the upcoming period.
Yes, it's going to be an exciting time.
Correct. Yeah.
At the moment, yes. So, well, if there are any more questions for Jesse,
There's one.
we'll do that. Last one? Oh, go
Yeah,
ahead.
there's one. So there's a question about the ranking of the Netherlands in terms of scientific. So do we know that?
Yeah,
Or
we
do
know
we
that.
think?
But I don't have it. I don't know it by head. But we built up a research report about the ranking. We are in the top ranking that is connected to the number of PhDs that we have already there. That is connected to the number of patents that we have in the Netherlands or that we have requested there. Of course, we can't be developing in China, but we are in the top ranking there, and there was research done on that level.
All right.
Okay, cool.
Well, there's one more question that I want to ask to you now. But if there are more questions for Jesse, we have time at the end of this first part to elaborate more. But for now, the last question, do you intend to support international founders to help start quantum startups in the Netherlands?
We are always open to discuss this. So we have the goal to boost the ecosystem there. It's important to accelerate the national industry there, but also we are open to have discussions about international partnerships and startups that wants to have a deployment in the Netherlands there. But we need to check out how that is fitting in the program and the guidelines that we have received.
Yes. All right. Thank you for this nice overview of the national agenda for quantum technology. We will see you later in this hour. Thanks again. And for now, we will continue with Florian Schreck. He's already here. But before we continue, I want to mention that there were some troubles at the start of this broadcasting on our website, but the embedding problem is solved at the moment. So if you're watching on YouTube, but prefer to watch it on our website, where you can also ask the questions in the Slido on the right side, then please go back to our website because it should work now. I'm very sorry for the inconvenience, but we're still here, and I'm glad that you stayed. And we will continue with our next speaker, Florian Schreck. Florian is a professor at the University of Amsterdam and also works at Qsoft, and he has a very interesting presentation. I will give the floor to you now, Florian, because we like to hear you talk instead of me. Go ahead. Florian, your microphone is on mute.
Interesting. Okay. Yeah. So thank you, Yvonne, and thanks for inviting me to this event and letting me speak about quantum sensing and computing with ultra-cold atoms. So let's start with quantum sensing. For example, sensing the flow of time, building a clock. Let's imagine you live 200 years ago, and the king gives you the order to build him the best clock in the world. Then you would most likely use a pendulum as your frequency reference to make this clock tick. And this pendulum is a macroscopic man-made object. You will never be able to build two pendula which tick at exactly the same frequency. And therefore, one day, the king will be late for his appointment with the queen. And then you have a problem. Luckily, we live in a quantum world, and the quantized energy levels of atoms provide you with an ideal frequency reference, namely the frequency of the electromagnetic radiation that's needed to drive transitions in this atom. And using these atomic transitions as quantum sensors for time or magnetic fields has lots of advantages. First of all, an atom of a certain isotope is identical to all the other atoms of that specific isotope. So you have truly identical sensors given to you by nature. And these atoms are very small, so they are suitable to build miniaturized sensors. And you can go way beyond just using the quantized energy states of the atoms. You can use many more quantum tricks to improve your sensor, engineer the quantum state and the readout protocol to be very sensitive to the desired quantity you want to measure and less sensitive to other quantities. Now, you can use many different systems to build quantum sensors: molecules and V-centers, nanomechanical oscillators, hot atoms, ultra-cold atoms, trapped ions, and you can measure many different quantities. And 3 of these types of sensors will be explored within quantum delta NL. Now I will mostly zoom in onto ultra-cold atoms, which are very well suited to measure the flow of time or accelerations. Let's build an atomic clock. So we want to use the frequency of this optical atomic transition. Which transition should we use? We need, for a very good clock, a transition with high frequency and narrow line widths. Optical transition with millihertz line widths would be nice. We want a large signal from our clock, so we need to use many atoms. But these atoms shouldn't touch each other because that would shift the transition frequency. So we need to use a gas of atoms. Now, usually at room temperature, atoms in a gas move around with hundreds of meters per second velocity. That's bad because the Doppler effect will shift this transition frequency around. To avoid this, you need to cool these atoms to essentially stand still. And we do this in machines like this one, not in normal cryostats. This is a vacuum chamber. And then one side, you have an oven heating up a sample of strontium such that individual atoms evaporate and form an atomic beam. And we slow this hundreds of meters per second fast atomic beam down by a counterpropagating laser beam, which scatters photons on the atoms. And then we use additional laser beams to push the atoms into the center of the vacuum chamber and cool them even more. And here, this glowing cloud, that is a cloud of strontium atoms nearly standing still. And we can trap these atoms now in a so-called magic optical lattice. It's like trapping, confining eggs in an egg carton, and then the atoms are truly standing still. Now, to measure their transition frequency, we just shoot a laser beam onto these atoms. And if the laser has just the correct frequency, the atoms will get excited and we can see this. But if the laser drifts away in frequency, then not as many atoms will get excited. We notice this and can pull the laser back to the correct frequency. And that's it. That's our optical clock. Now, many people are not happy with a clock that ticks at 400 terahertz. And those people then can buy an optical frequency comp and use it as a clockwork to translate this high optical frequency into, for example, the microwave frequency domain, where electronics can use the signal to, say, move the hands on the dial of a clock. And the best one of these optical clocks, they're really, really precise. They would go wrong by only 1 second over the lifetime of the universe. And you can do amazing things with these clocks. Remember the movie Interstellar, where astronauts approached a black hole? The ones which got closer aged slower because of gravitational time dilation. Now, unfortunately, we don't have a black hole close to Earth and can experience this effect in our own lives, but we have these super precise optical clocks, and they can sense a minusculous gravitational time dilation of the gravitational field of Earth. Let's say you live in a city next to a volcano, and you would, of course, like to know when the volcano erupts. And to explore the underground, you could build a network of clocks across your country connected by telecom fibers to compare the frequency of these clocks. And if now the magma chamber of the volcano fills up, the gravitational field above it will slightly change, and the clock will see this gravitational time dilation. You can notice it by comparing different clocks. Or here another use case. We all use mobile internet, and it works also because different cell phone towers are nicely synchronized with each other, and that happens also because of the satellite GPS and Galileo navigation satellite timing signals coming to Earth and synchronizing these cell phone towers. Now imagine there is a nefarious actor hacking or spoofing those signals, or just a solar flare wiping out these satellites. Then the cell phone towers would desynchronize, and we wouldn't have mobile communication anymore. But we can also synchronize these cell phone towers through the glass fibers of the cell phone network itself, and use signals coming from a very precise master clock, which could be one of these optical clocks. And then if there's a solar flare, nothing special happened. We would still have mobile internet, and that would save us losses of billion euros per day in Europe alone. If we have these nicely synchronized cell phone networks, we can use the cell phone towers to send out time-stamped signals to, for example, self-driving cars, which can use these signals then to determine their location to within 10 centimeters, which is, of course, very useful. Now, we want to push our research from the laboratory more towards these societal and industrial applications within Quantum Delta NL's Cat3 program. And we do this by building 4 quantum sensing test beds on these 4 technologies shown here. And we want to build up an ecosystem of developers, industries, and end users, and improve these sensors and develop applications. And one tool we have in our toolbox are open calls for new quantum sensor components or a wider range of sensors. Now, let's zoom into the ultra-cold quantum sensing testbed. Typically, these optical clocks nowadays are really large. We need to make them smaller and simpler. And this is something we already pursue in our quantum flagship project, IQ Clock. And based on this project, we push now further within Quantum Delta NL, exploiting the strengths of Dutch industry and research. In addition, we want to bring these clock signals to end users, make the access to them easier, because not everyone wants to buy a 2 million euro optical clock, but you can give access to these signals by telecom fibers, and we want to do this within Quantum Delta NL. Now, within our test bed, we will help industry to develop components for these optical clocks and also atom interferometers. And if you look at these systems, the most complex part are actually the laser systems. They are fragile. They are the reason why you need to babysit these clocks nowadays with PhD students to make them work at all. So we want to exploit here the strengths of the Netherlands, photon delta, and replace the free space laser systems by photonic chips with the help of Leonics and Quicks, or the standard lasers with perhaps chip scale lasers developed at the University of Twente by Klaus Boller. We will collaborate with ESA and ESTEC. They are really interested in sending these clocks to space, and our first idea of collaboration is to develop compact atomic sources. Furthermore, we also will explore atom interferometers for inertial navigation, and that we are going to do with TNO Den Haag. And to ease the access to these signals, we will work together with Jérôme Culmay from VU and VSL and Eurofiber and SURF to distribute these signals across to interested partners in the Netherlands. And we will support application development, terrestrial navigation, security applications, but also applications in research. Now, let's go expand briefly beyond just ultra-cold sensors and take also a brief look at the other sensors, spin sensors first. So at TNO in Delft, they use NV centers and silicon-based spin sensors to measure magnetic fields or electric fields or pressure and temperature and so forth. And they have, for example, built a scanning probe microscope where they can guide these spin sensors across a surface and measure time and especially resolve these fields. They want to show the usefulness of these sensors for semiconductor metrology, biomedical research, positioning and navigation and defense applications. And if you want to know more about this, please contact Clara Osario Tamayo at TNO Delft. So then we have the mechanical quantum sensor testbed, where Simon Gröblacher is essentially using MEMS sensors, just like the sensors you have in your cell phones to measure accelerations. You see here very small masses levitate or held in place by springs. But now, in contrast to the sensors already in place in phones, this testbed will explore quantum effects to enhance these sensors, and they will build a multi-user facility for testing and benchmarking these sensors also in a real-world environment, and of course together with industry and academia and government. And then we have the superconducting sensor testbed by TNO Den Haag. They have already fabricated amplifiers based on superconducting Josephson junctions. They can amplify RF signals. For example, they've built a quantum-enhanced RF front end for wideband spectrum monitoring. So this is initially, at least, mainly defense applications, but that could also be useful for an airport radar system in the long run. And TNO Den Haag is also looking into inertial navigation, for example, sensor fusion between classical sensors and quantum sensors, like we are developing them in Amsterdam. Now, please contact the people on which are responsible for these testbeds if you want to know more. So far, I spoke about quantum sensing with ultra-cold atoms, but in the beginning, I also promised you to speak about quantum computing with ultra-cold atoms. So let's do this. If you want to build a quantum computer, you need to replace the classical bits by quantum bits and classical gates by quantum gates. Let's speak just about the bits. A classical bit is just 1 or 0 represented in an electronic circuit by voltage of 5 volts or 0 volts. In a quantum bit, you use 2 different quantum states, and any viable state of this quantum bit is a superposition of these 2 states. And you can best visualize this as any point on the surface of a sphere. For example, North Pole is state 0, South Pole state 1, and the equator is a 50-50 superposition of 0 and 1, and the angle along the equator is a certain phase that your quantum bit might encode. Now, a big difference between these classical bits and the quantum bits is that classical bits are intrinsically noise resilient. If your voltage is slightly deviating from 5 volt and going to 4.5 volt, you still know that your classical bit is most likely in the state 1. Yeah, but if a a quantum bit is influenced a little bit by noise, which means this orange spot here on my sphere representing the quantum bit is shifted a little bit to the side, then you don't know if this little shift came about as a result of a quantum computation and is really desired, or if it's just an artifact of noise. So these quantum bits are not intrinsically noise protected, and that's a difficulty. So there are algorithms where you can merge like many real qubits into one logical qubit that is noise protected. But even for these algorithms to work, you need to start out with very good quantum bits. And this is where atoms can come in, ions or neutral atoms in, as I have shown them to you in clocks. You just use two states of your atom as 0 and 1, and these could be the two states linked by a clock transition. And actually there is a nice relationship between clocks and quantum computers. Now, if you use this transition, which you used as your clock transition, if you want to make a better clock, you need to have these levels very well defined and very noise free. So if you build a better clock, you automatically build a better qubit, yeah? At least once you get single access to individual atoms. And the clock interrogation is nothing else than single qubit operations. And what we are exploiting here for the quantum computer is the same as what we exploit for clocks. We are given by nature identical qubits, which we just shouldn't mess up. Yeah? Okay, so in principle, a clock is a simple quantum computer, and a quantum computer is a fancy clock. Yeah? And with our neutral atoms, what we can easily do is scale up our system to many qubits, which, as long as we don't mess them up, are really truly identical, given to us by nature. And we do this by holding these individual atoms in so-called optical tweezers. Yeah, no need to know the details. These are just little laser beams which can hold the atoms in place. And then to make these atoms interact with each other, to make gate operations, we just excite these atoms to highly lying atomic states where the atoms are getting very fluffy and feel each other and can exchange quantum information. And we are pursuing this in Amsterdam since 2 years or so within the Quantum Software Consortium, and have built a strontium neutral atom quantum computer / simulator. And also Eindhoven was since years interested, and they have a rubidium system where they have little clouds of rubidium atoms in optical dipole traps that they can link by these excitations I talked about. And now we joined efforts, we merged our two teams, and we are in the process of translating all the know-how that we earned in Amsterdam about strontium quantum computers to Eindhoven. We are building up an enhanced version 2 machine there, which will be hooked up to Quantum Inspire. And in Amsterdam, we will use our machine as a pathfinder machine. Here's a result from Amsterdam. We have now very nice control of a 4x4 array of tweezers with individual atoms inside. And currently, we are enhancing our system to get to about, we hope, 100 tweezers. And we have already built all the laser systems needed to make these quantum gates. So we are moving them over to the main machine and try to make this work. And now I told you a quantum computer is essentially a fancy clock. So the computer we are going to build in Eindhoven, the one hooked up to Quantum Inspire, it needs these laser beams precisely on the correct frequency of the strontium clock transition. And yeah, building yet another clock in Eindhoven to make this possible would cost another 2 million euros or so. It's not really, yeah, it's not so easy. And misusing the quantum computer as a clock, it's possible, but it's not the best. You don't get the highest quantity. So in Amsterdam, we will have a clock. Why don't we transfer the signals? And that's where we are working with Jeroen Kulme from VU and partners like Eurofiber to transfer this precise frequency of the strontium clock in Amsterdam to the quantum computer in Delft. So we are using a quantum clock for a quantum computer. And I like this idea very much to collaborate across different pillars within quantum delta NL. And I think we can strengthen this in the future. Okay, and this brings me to the end of my talk. I've explained to you how ultra-cold atoms can be used for quantum sensors and computers. You've seen that clocks are good for network synchronization, positioning, underground exploration, inertial sensing, and they give rise to quantum computers where you can relatively easily scale up to many, many qubits. And I've described to you what we want to do within Cut 3 and Cut 1. So thank you very much for your attention, and I'm curious to have your questions.
Yes, thank you, Florian. Great presentation and awesome work coming up in the coming years with quantum delta NL. So quick question. So you mentioned a couple of use cases, but who do you think will be amongst your first customers for the coming use cases?
Okay, so we are discussing this, of course, already with some people. So yeah, don't know how many details I may already say. So of course, one application is security, just our networks to make them more resilient, to make them more stable. If you have hackers or so, or spoofing GPS signals, you want to avoid that your network is taken down by this. This could be all kinds of services running in existing internet networks already. So if you would build an additional time distribution system on top of that, that could be a commercial service to some people. And also this navigation system would be for sure interesting for, like, I mean, I didn't talk with KPN yet, but I guess they should be interested in offering such a service through their cell phone towers.
That's an interesting bridge you're making, Florian, because we have someone who worked at KPN coming up. So we might hook you up together so you can have a chat on that. I don't know. But thank you. We'll address more questions in our Q&A. But after
maybe you can ask the last one, because this person already asked it in the first 5 minutes. Nice question for Florian. Maybe I'll just mention
but I want to keep that one to also.
Keep it to the end. Sure.
So
all right.
It's not only about us
Lars has to wait then.
Yeah, let's wait a little. Let's save that one. Remind me of that one if I forget it. So, Florian, thanks. Great to see the work coming up in the coming 7 years of Quantum Delta. And we're on to our next speaker. And our next speaker is not so attached to Quantum Delta. It's Jaya Balu, former CISO of KPN, now CISO of Avast, still the quantum ambassador of KPN, and still in advisory boards of the quantum flagship in Europe. So she's been working over the past years already, doing stuff in the fields of quantum, and it's interesting to hear what her ideas and vision are in the fields of quantum technologies without having all the plans spread out. So Jaya, thank you for joining, and take us away.
Thank you. So first of all, it's a pleasure to be here. So thank you very much for inviting me. Sometimes being freed from the burdens of like knowing a very specific streaming or track makes you question a lot of the things that you assume to be true or taken for granted. So basically, I wanted to ask the question to you, what if? I mean, I know we have a national quantum agenda. I know that we're all very happy that we have 615 million that's been granted, but how can we take a look at potentially different ways to do the same things and maybe get some inspiration from approaches that are used elsewhere? So if we take a look at what the things are, you're basically traversing a fine line. And I spoke to Stephanie Vayner earlier today, and you're traversing a fine line, I think, between inspirational or a complete batshit crazy. So let's walk down that road and see which one of these goes on either side. So the first thing that I thought was really interesting is this ability of really industries outside of Europe to do a very good job, not only of pushing the envelope in terms of innovation, but also really, really doing a great job around how they communicate their findings. And one of the things that I thought was really interesting was really Florian just talked about qubits, two orthogonally different states, and use that as a basis for building a quantum computer. But what I thought was also exciting is to look for more than two states. So qtrits, which are three orthogonal states, or even qdits, anything more than multiple orthogonal states, to think about new topologies to really figure out what else could we be doing, and then making it accessible to a wider group of people. So I just gave some examples from Berkeley and Sandia, not only of the innovation that's happening there, but also the communications capability that they have to make these things on Twitter, on news, and et cetera. I think they do a very good job of doing that. So it would be interesting to know how much we could push the envelope. What if we could push the envelope even further, both in terms of exploring all types of hybrid approaches with a quantum computing testbed, and then also look at increasing ability. I mean, Quantum Inspire is wonderful. So could we perhaps increase accessibility in other ways to a wider set of individuals who not only want to try things out, but also, like Florian mentioned, look at what great things can happen when you collaborate, and look at what even amazing things can happen when traditional competitors collaborate. So what if we did that? And maybe another what if question is, just to go to the next slide, what if we rethought, we talk about quantum communications for quite some time. It's still, I think, very much core, foundational to all the things that we want to do. But what if we made that accessibility, the democratization of something quantum internet, which, traditionally when we looked at it, I mean, when I was at KPN, and I'm still the quantum ambassador, but when we looked at it, we really thought about it from the principle of giving folks access to our traditional core network, dark fiber, putting QKD devices on there and giving them that. But that's not really accessible to a wide variety of folks. So just to completely, and this could be in the realm of batshit crazy, but what if we could make something like this much more accessible to a wider group of people? And I just put together, an idea of freedom internet. What if we could give not only QKD on a core network, but include it with PQC, so have a hybrid quantum safe network, and then drive towards, even for, if you wanted to go QKD all the way, drive for clients that would be accessible, affordable to a wider variety, a larger audience than just the traditional enterprise or critical infrastructure oriented users, and think about bridging that even further out. So, if we go take this from this, again, approachability, democratization, and we take it one step further, I do think that hybrid approach using post-quantum cryptography is going to be necessary, not only because of the way that we've built the internet, but our need to start now in order to have a strong defensive position as a country. This is not a small thing. It certainly will not be easy for the majority of enterprises and infrastructure providers. Infrastructure providers are not known for their agility and their ability to deal with change, even when it comes at a cost of security and safety. So I think that we really need to think about, how do we get all of our infrastructure ready? And part of this could be, already thinking about deploying PQC technologies and following the NIST algorithm set already now that we're in round 3, just trying stuff out at a national perspective, and then already having use cases that are available to be consumed by this huge thing. So even if you do it as a proof of concept or proof of value, what if we could get a full communications infrastructure that's capable of being digested by these different folks? I think that, like having post-quantum cryptographic VPNs, this is something that's already available. You can already do this with a couple of different providers, also notably WireGuard. So I think it's about taking this and making it part of the core availability from your ISP or provider. And then if we go out even one step further, I know that the space budget, and again, this was also something I was chatting about with Steffi, they got a lot of money. So they have way more money than the 615 million. I don't even think that we fully understood all of the different use cases that we can do with space. And, when Dimitri was at ABN and I was at KPN, we participated together in this joint project to look at critical infrastructure use cases that could be used when you had this QKD infrastructure out in space. But, maybe there's something else we can do. What if, one of the biggest problems we have is this cost of infrastructure in space and all this ridiculous amount of space junk and the inability to do repairs in space. But what if we were much more efficient and we treated it like we treated the cost of infrastructure in the early days of the internet? So what if we took all of the different LEO constellations that Elon Musk and Jeff Bezos and Richard Branson and someone else's billionaire is building, and we combine that LEO infrastructure, who don't play well with each other and do not interoperate, and found a way for them to share communications securely at a geo level. So at geo orbit, we took all of the LEO communications traffic, and just like having a backhaul link or a interconnected router, that we would then take those signals, uplink them through a geo layer, and then do that, all that communication using QKD. And I don't know what physicist doesn't like the idea of lasers in space, just fun. But I think it might be something to put out there as something that would be a possible cooperation. So not investing huge amounts of money, but maybe making the use cases more transparent and available, and working together with the larger budget that's probably been afforded to ESA and other space-based trajectories. And another what if, again, in order to increase our capability to innovate and to make it clear why you should do what, one of the things that I thought was really good about the NAQT, the agenda, was that there were some very clear missions for health and for agriculture, energy, safety, and mobility. What if we could take some of those wonderful goals, chunk them up, make them slightly smaller, and then do something that would be transformative, but also inclusive for society? So we chunk the problems up into smaller problems, and we make them a sort of X Prize award. And we have just part of that 650 million available to give out for solving some of these societal challenges that we had, where the application of quantum technologies could be a game changer. I think that we very often tend to leave the home innovators out. And in quantum, it's easy to see why, because access to some of the technology and infrastructure is particularly pricey. But again, if we could just use the energy and the knowledge and the creativity that's already there, that would be a huge win. And just by making it more accessible, you draw people in. And on that note, to draw people in, another very good example that I thought was effective for something that was also difficult for like the masses to engage and be effective in is, I thought, we have a couple of subjects where we have a horrible shortage of individuals that are capable of entering the workforce, doing innovation, doing all the stuff. Cybersecurity is no exception, but it's really predominantly because the STEM funnel for science, tech, and math and engineering, that it's really small. And one of the things that we just talked about was the fact that there's not enough knowledge at the lower levels, but it's not just about the lower levels. If you're somehow out of the educational system and you're somehow mid-career, there's also not an easy accessibility. So why can't we do something like that was done in the Netherlands already for artificial intelligence, which was the national AI course, try to do something similar for quantum? And there's plenty of ways to be quick and agile and, get content out there quickly. Maybe we can grab stuff from Coursera. But my point is to increase the STEM funnel. You can't just look at the traditional education mechanisms for that approach. Of course, you have to do that because it's available and the infrastructure is there. But going beyond that to make it more accessible to all people, also people who are mid-career doing something completely different, I think this needs to be something that needs to be considered. Also, I hate to be the one who brings up diversity and inclusion because it's talked about everywhere else and sometimes tiresome. It has to be about quality. What's always amazing to me, though, is that when there are actually initiatives that have chances of success, that they don't necessarily have the funding. So a potential area, there's already, women in quantum stuff, and I now spelled it as wicked because it is. But it would be really good to make sure that if there are already initiatives or already groups that could play a better role in increasing diversity and inclusion, let's make sure that they get funded and they actually have a chance of succeeding in their missions. I think it would make everyone more happy, and it would make it an easier thing to do for us to get engaged and get involved. So thank you. And just ask yourselves, what if?
What if? Thank you, Jaya. Nice going. It's always a pleasure to watch you present because you bring the right amount of energy. It's so very, very good. We have an interesting question from the audience, and the question is, you talked about space, so the question came up. Is there any party that's already looking into cross technology in space, like quantum resistant ledgers or quantum resistant solutions that you know of?
No, but I think ESA is definitely doing stuff. So when we say any party, of course, there's the European Space Agency who's been doing all kinds of stuff with QKD and in space. When you say ledgers, I have to think of blockchain ledger. But they have been, if you take a look, there's Operation Skylight, SCY Light, where they tried to do a QKD pilot. There's also several European programs that have been doing the same. And of course, there's the Chinese innovation and all different types of countries who are doing this from a national critical infrastructure perspective. So there's more than one quantum solution for space that's already been deployed by multiple countries. But the point is that they're not necessarily viable because of the cost of deploying something in space and the use cases for, okay, great, now you've put something in space, who's actually going to use this and pay for it? This is a bigger problem. And frankly, if we don't understand the product market fit for this, the science here is less relevant because it's seen as a nice science project rather than something that's going to bring in money and have continuous and incremental improvement and innovation. And that's what you really want. So if we really want to get everybody ready, we need to make sure that we understand the economics and can attract the right business cases towards solving some of these fundamental challenges.
True. That was really one of the let's say, biggest points that came out of the critical project that we were both together in. So yeah, agreeing that. So there's this huge challenge, this big gap of the high-tech industry and the end user, where you don't want to pay 30 million just to have a QKD link. It's just way too much.
But again, so the smart way, I think, and no one is doing that yet, is to find a way to take this payload that's already going up there. Elon Musk is putting, 30,000 satellites in low Earth orbit. And the only thing that can see all of these different satellite constellations in different areas of low Earth orbit is something that you could put into geostationary, which then has, basically the line of sight, if you will, for all these different constellations potentially. So the cost of deployment can be significantly decreased because it's going to be shared across these multiple constellations, and they don't like sharing their data. So using QKD or PQC to get to ground, combination of this. So using the lasers in space and using the radio to ground, I think this would be a really feasible combination, a hybrid combination to make better use of some of this infrastructure. And again, like the infrastructure is the problem. In the early days, we had dial-up networks, we had, BBS systems. That's what we are going to look at for space for a while, until we figure out how to make use of all of it and interoperate and share traffic and make sure that even when we share it, that it's still secret for the parties that are communicating. It won't be scalable, it won't be affordable, and it certainly will never be democratized. So.
Yeah, interesting thought. I'll catch up on you on that.
Yes, thank you, Jay. Yeah, we still have time left for this first part, but I want to bring back our other speakers. Florian and Jesse is also still here. Yeah, we can conclude that we can look into a very bright and exciting and still unknown future of quantum technology. And at least in the Netherlands, we did a good job by awarding Quantum Delta NL to boost this development. Yeah, and we hope that companies will co-create new applications with science very soon. We have some questions still left from our audience. Let's start with the one who was the first.
It's up. So this is also Yvonne, a question to the audience. So I just activated the poll. So if everybody could either go to Slido or just vote on your right, if this is the right or this is the right, I don't remember anymore. But let's see what the audience thinks on what quantum computing qubit type would be the first one out there to become scalable. So where would you put your money on? Where would you bet on? So it's coming up. Yeah. We have a couple of votes coming in. Most of them still going towards superconducting. I just added the atoms of fluorine in it as well. You're still getting there, Florian. So people are trusting you to pick up the pace and create this quantum computer. So it's cool.
Yeah, so the poll is, what quantum computing qubit type would you bet your money on? Superconducting, Majorana, ion traps, photonics, strontium atoms. And then in the meantime, there was another question for Florian. Which technology is probably the best scalable solution to generate and read qubits? What will be the future of photonics in quantum technology? So after the poll is done, Dimitri, you'll let us know, and then maybe Florian can help Lars out.
Should try to answer. I mean, I'm not an expert in photonics for quantum computing, of course, so I just know about companies like PsiQuantum, which make big claims that they are developing a large and scalable quantum processor. I do know what Quix does. They have a 12-channel quantum processor. So that's definitely feasible. I do know that this technology, you still have these waveguides which have a maximum radius of curvature. In the Onyx or Quix case, it's about 100 micrometer radius of curvature. So you can't squeeze too much, of course, on a chip. So there will be a limit, just as it is the case for all the other technologies too. So I don't know. It also, okay, the smallest qubits I know of course, are the electron spins and the silicon qubits. Leaving for example, explorers. They're done with normal silicon fabrication methodology. They can be built up quite quickly, and then the question is, can you get them good enough? So it's always a trade-off. The ion qubits are large because the spacing has to be good, but they are super good in quality.
All right.
Yeah.
Dimitri,
so let's.
Do you have?
Let's see the results. So most people are betting on the superconducting still. It's probably also the most famous one. But photonics is a close second, and then third, Florian, you're even further than the ion traps. So people are betting on your quantum computer. So it's a great thing. But Jaya, what do you think is the most? Where would you put your money on?
Yeah, I think, look, honestly, guys, I feel like I am also not qualified to answer this question, but where I would put my money on is anything that we can do as a community to get beyond this noise problem and get to stability. So the question is, should we even be looking at it from this perspective of choosing a type, or should we be examining it from a perspective of like being incredibly opportunistic and looking even at potentially new materials? Because even with the superconducting qubit architecture, there's been, I think there was a TU Delft discovery, maybe Jesse, you know about this, about the geranium chip or different topology.
I know.
Yeah. So I think we're going to potentially like not wind up with what we have now as options, but
the question is it that black and white for now? As the example Jaya also gave in her presentation, to for instance, PQC versus QKD. Sometimes there's a fight between the people that work on PQC versus QKD. But as Jaya said, you need to work together. The technology needs to work together. And this could also be in that area of development of computers there. I think we will learn from the different technologies what's happening there, and probably that will support each other in the different areas and the different angles.
Yes, indeed. So the cooperation between different research fields is very important. I think Quantum Delta NL supports that. All in the Netherlands, we have all our different expertise as well. And there's also a question from the audience for Jesse. What's the relationship with Quantum Delta NL to the EU Quantum Flagship Program?
There is not a direct relation at the moment, but the QFlag program is really important, and we try to sync the developments there on national and international level, because it would be stupid if we do different things, what's happening on international level, but also if there are developments going on in Quantum Delta, how can we support on the QFlag programs that are going on? So we are focusing there also on, and the entities that are executing the programs within Quantum Delta and that are connected to the QFlag program are also involved on these different levels. So it's important to keep each other close and work jointly on this topic.
Yes. Well, and there's we have a little treat left, because we have a couple of minutes and Florian is still here. If the audience still wants to interact with our speakers at 15:45, well, that's Dutch time, right? But in 3 minutes, we start the wonder.me get together. You can click the link below on the website, below this movie, and then you can still ask your questions to Jaya, Jesse, and Florian. But before we do so, Florian has a virtual tour of his lab, so you can actually see the science from your home. Florian, can you introduce it?
Yes. So this is the lab of our quantum flagship project, IQ Clock, which is the baseline of our also-called quantum sensing testbed. And I mentioned to you, we need to simplify these optical clocks. And one way to do this is shown on the slide you see here. We try to entice our strontium atoms to directly emit a laser beam of light on the optical clock transition. And okay, I don't have time to explain this, but this would make a simpler clock. And in the video, which you should see now soon, you will get a guided tour through this lab.
The IQ lab. Today I'll show you a little bit what we have around us. So we are still in a building phase, so it's a little bit of a mess, but there are also good stuff. So let me start from our machine. We are building a kilohertz clock, so you don't see it from here, but the atoms are starting from an oven that is like below there, and they then travel vertically, and we use blue and red light, the blue you can see, to manipulate them, and prepare them for the final stage that is in a cavity that is more or less at this height. Also a little bit of red. Where they then are going to super radiantly emit, and this is the signal we are interested in. We use different optics. You can see here different distribution systems to prepare the lights we need, and we control the different stages thanks to software. So here it's in particular the one related to our experiment, and we also monitor the different lasers using cameras, and I'll show you where the lasers are. So first we arrived to the electronics cabinet. So here we have the different RF amplifiers and the frequency generators to control again the frequency of lasers and prepare them. And the real subjects are here. So we have blue, as I told you, and red. And let me see, and I can show you. Okay. Oh yeah, thank you for this short introduction. I can show you other people working here. So perhaps we have our Camila. And our Stefan and Shen, and Shen in the other lab. So yeah, thank you for this very short tour, and I hope you enjoy.
Yes, that looks great, Florian. Very nice.
It was Francesca Fama, one of our PhD students.
Yeah.
And after the pandemic, you're all welcome to visit us.
Come
Looking
to
forward.
Quantum Amsterdam and see what we are doing here. Thanks everyone again for your great presentations and the explanation of the national agenda for quantum technology. What would you do with 615 million and what will you do with 615 million? If you back home have still questions for these speakers and want to chat a bit more with them, very casual, please click the wonder.me link below. And don't forget to take some time to hydrate, go to the toilet, stretch your legs a bit, because we'll be back for the second round at 4 o'clock in approximately 15 minutes. And then you will hear what Harry Buurman will do within the Quantum Delta NL, and what Gilles Brazard, not in the Quantum Delta NL, but all the way from Canada, would do. And hear these two inspiring speakers after the break. See you soon, and enjoy. Our event 615 million for quantum. Proposed, approved, action. Quantum Amsterdam is the innovation hub for companies to explore and develop quantum software, technology, and new applications. Our mission is to connect academia, industry, and society by facilitating knowledge exchanges and innovation. Therefore, we organize meetup events, workshops for companies to learn more about the possibilities of quantum technology, and our knowledge partners such as QSoft, CWI, University of Amsterdam, Amsterdam University of Applied Sciences, AMOF, and Surfsara have already set up collaboration projects with the industry. If you are interested and want to learn more, please visit our website www.quantum.amsterdam or contact our Quantum Innovation Officer Koen Groenland. And for now, please enjoy the rest of the afternoon with our big meetup event. Yes, welcome back everyone. I hope that you have recharged for the second part of our big meetup event. 615 million for quantum proposed, approved action. Yes, we are now with two other speakers. One is Harry Buurman and the other one is Gilles Brazard. Harry is from within the Quantum Delta NL, so he can actually share his plan on what he's doing within the National Agenda for Quantum Technology, but Gilles isn't within the Quantum Delta NL, so he will tell you what he would do when he would have 615 million for quantum. Both inspiring speakers, so enjoy this afternoon. And for now, we will start with Harry Buurman, professor at the University of Amsterdam and director at QSoft. Harry, how are you?
I'm fine. I'm actually also affiliated with the Center for Mathematics and Computer Science, where I have the Algorithms and Complexity Group. And indeed, it was quite a big surprise, and we all had hope for that the Quantum Delta would get funding, and that happened. So that was really fantastic news. But then you also had this event where you asked me to say something about what I would do with a whole lot of money, and of course you can come up with all kinds of a little bit sleazy ideas on that, like big cars and boats and helicopters and all that. But I won't bore you with this, because the truth is we already have a fantastic plan called the Quantum Delta Netherlands, which we have worked on for many years, and in some sense we have been preparing for this for the last 10 years, or maybe even more, to lead up to this, and the whole field has been leading up to such a big step forward. So in a way, the answer is fairly easy. What you do with it? Well, this is the program Quantum Delta Netherlands that we have already built, and I will tell you a little bit about that. But before that, let me say a little bit about how it sort of leads up to that, and what my role in all of this is, and what my interest in this is, and that is on the quantum software side of things. So not on actually building quantum hardware and qubits, and of which you heard talk in the previous session, but really how to make good use of this this quantum hardware, the one that is available, and the one that will be available hopefully in the near future. So, but first you have to realize that programming a quantum computer is really done in a fundamentally different way than programming a classical computer, just as building one is done in a fundamental way than a classical way. And you probably all have heard of these notions of superposition and interference and entanglement, and those are really needed in order to make good use of your quantum computer. And when you do, the results can be spectacular, but there also is a bit of a downer, because it's certainly not always possible to speed up your computation using a quantum computer. Actually, we will see in the course of my talk that for many problems it's not at all useful to use a quantum computer. However, much effort is needed to uncover the power of these quantum devices, and that's why 5 years ago we launched a research center, QSoft, together with CWI and the University of Amsterdam. And we recently had our 5th year anniversary with, among other things, the inauguration of the Turing Chair by Gilles Brazard, who I'm very happy and honored to speak in the session after me, or in the talk after me. And then in 2017, sort of maybe a precursor of the Quantum Delta NL, or maybe a small seed of that, was the gravitation grant called Quantum Software Consortium that we obtained together with Leiden and Delft. And the idea in this consortium was to co-develop, I think is the nice term, or I call it a research cycle. I will also say a bit more about that. Quantum algorithms and hand in hand with that, the quantum hardware, and somehow co-develop these two and work and understand what is needed from both ends. And so this started in 2017 and has been happily going on since. And let me tell you a little bit about QSoft, and it's very interesting to see how that developed over the years. We have at the moment about 25 permanent faculty. We are spread over CWI University and also the VU University. And we have about 20 PhD students and 20 postdocs. And so we have been growing quite significantly in the last 5 years. And the whole area, the whole field, the whole institute straddles the fields of computer science, physics, and mathematics. And actually that's extending even a little bit to chemistry and even economy and business school. And as you can see here in the middle, these are the 4 initial themes that we set out to do in QSoft. Here on the top, you will see what we call quantum simulation or few qubit applications. And here the idea is to interface with small qubit systems that are available in the lab and somehow interface and try to program them in some very rudimentary way to do tasks that are interesting. And then here at the bottom, you say a theme called quantum algorithms, where we are dreaming up a little bit bigger quantum algorithms and protocols that could be run on near future or in the future quantum computers that have so-called error-corrected qubits, sort of stable qubits that don't get disturbed over time. And it's important to also think about what you can do with the devices in the future, a little bit in the future, because that way you can still feed it into theme 1, where you talk with the actual hardware available now. Then here on the right-hand side, you see cryptography in a quantum world, and that is a theme that deals with how to make the world safe again once there are quantum computers that can break certain cryptographic protocols that we have running nowadays. And actually Gilles Brassard was one of the first, maybe the first, who actually developed protocols there. And then, so I will not say much about that theme. And then here on the left-hand side, we have quantum information science, which really is the fundamental and the fundamentals, I should say, of quantum computing and quantum information, where we really develop the theory and the building blocks. And now all that is extremely academic, but nevertheless, in the past couple of years, we have started to work together with industry. In particular, we have project with Bosch, ABN AMRO, where Dimitri is also partially settled, and also recently with Toyota. And for all these companies, the question really, what they wanted to be answered was, how can quantum computer help my business? How can it help in our surroundings? And if so, then can you please help us become quantum ready, in the sense that if a quantum computer is available, or one that is at least a little bit bigger than we have currently, then we would like to have a running start and use that immediately. And so because of the success of that, we have now started a new research line, which is not yet incorporated here in this picture, called Quantum for Society and Business, that predominantly deals with these kind of questions, and not only to industry, but also to society at large. At the same time, when we decided more or less to have a research line like this, we also started up Quantum Amsterdam, which you are now indeed visiting. And you have been hearing probably a bit about that, and you visited the websites. So I won't say too much about it, but Quantum Amsterdam is a hub that sort of deals with the hardware and the software, and it's an application hub where you can come to if you have questions about this. It is helping facilitate to build an ecosystem, of course, in the first place around in the neighborhood of Amsterdam, but of course also tying into the bigger ecosystem in the Netherlands. And it is enabling this interaction between industry and academia that you saw already a couple of examples in my previous slide. It's organizing workshops and outreach and meetup, and it's a startup generator. And indeed, for all questions, go to Koen, who is our quantum innovation officer, or Yvonne, or talk to Dimitri or Martin. And we also coordinate with the Dutch quantum landscape. So this sort of ties into the larger quantum delta, of which you heard Jesse Roberts saying already something. So let me say a little bit about that and sort of give you my point of view on that. So the program, as I already said, we have been working on for quite a long time. It has these 3 catalysator programs, one for quantum computing, one for the quantum internet, and one for quantum sensing. And here you see a nice picture of these 3 CAT programs. And then there are also 4 action lines that you see here below. The first action line is realization of research and innovation breakthroughs. This is sort of this blue ball that you see here in the middle, and that deals with fundamental research that needs to be done in order to sort of perturb to the surroundings and to the CAT programs. AL2 is an ecosystem development and market creation, and that somehow ties in really well with Quantum Amsterdam. Then the third action line deals with human capital and education, which in some sense speaks for itself. We really need people, and we need many more than we have currently. So if you're interested, please connect up with us. And the fourth action line is this connection with society, and it really ties in also with this 5th research line of QSoft. And then in 2020, somehow as a precursor of the announcement that the Quantum Delta got funded, we got already some pre-seed funding, you might say, the startup grant, where some of the program was allowed to start. In particular, what was allowed to start was some work in the CAT1 program on quantum computing, where we were allowed to start working on use case developments together with TNO, and to really do this co-development interaction with the hardware, with Delft on the system that is key for the Quantum Delta, namely this Quantum Inspire system. And you see a little bit a picture here on the right. Then we also started on working on use cases for quantum networks. And within this action line to this ecosystem development, we could start up really seriously Quantum Amsterdam, and also something that we call the Quantum Application Lab, that somehow is there to develop applications and use cases for industry in combination with the academia, and also again trying to implement that on Quantum Inspire, or perhaps also other systems if and when they come available. So this is in a nutshell the Quantum Delta Netherlands, and also sometimes called the National Agenda for Quantum Technologies. You can download the program and see for yourself what the plans are exactly. And if you have questions, I'm happy to answer them. But I also want to say a little bit about what I want to do within this Quantum Delta, and the things that I personally find very interesting. So I'm zooming in now a little bit on the computational part of this. So on this CAT1 quantum computing and simulation part of the Delta, and in particular, not on the hardware, but on the software side. And a question that I have been thinking about, well, basically since I was born, at least academically speaking, was what computational speed up can you have with a quantum computer, or in general, what can you compute with a computer? But now it has become more of a question, what can you do with a quantum computer? And there are luckily a couple of nice applications that we know that run on quantum computers. The first one was sort of the thing that made it all tick, the result of Peter Shor, that shows how you can break a lot of current cryptography. And then I already alluded to that. There was a fix. Actually, the fix was there before the break. And that was due to Bennett Brassard, and also a little bit later due to Eckert. quantum cryptography, making cryptographic schemes that actually make use of quantum physics itself to be secure. Probably Gilles will say a little bit about that. Then there is efficient communication, and we know that if you have an internet, if you have a quantum channel, then you can do certain things that you cannot do classically, and this all manifests itself in this quantum internet, and there are very nice things you can do there. Then applications, we know probably the ones that we see first, and maybe that will be important the soonest, are those of simulating nature itself, because nature is quantum mechanical, and we don't know how to simulate it very well on our classical computers, but we do have some idea on how to do that on a quantum computer, and that allows us to study chemistry questions and material design questions that we currently cannot answer, and hopefully we can answer them then. And also perhaps it will once help develop new medicines, although that is a bit further into the future. And then there is a whole slew of applications that we have for optimization and machine learning, which are important for society and industry. And I often get the question, what problems have a quantum speed up and which ones don't? And this is really very deep questions, and there really is no easy answer to that. But sort of the easy answer that you could give is that there are three categories, namely those problems that have an exponential speed up, like the factoring algorithm of Peter Shor and the quantum chemistry simulations. Then there are problems that have a polynomial speed up, like backtracking, search, and satisfiability solvers. And then there are the problems that have no speed up at all. And here you have to think about problems that are extremely hard and problems that are extremely simple. And so the truth is also that for many problems, we actually don't know in which category they fall. So here is schematically given how that works. We have the problems that have no advantage, polynomial advantage, exponential, and unknown. And most of them actually are unknown. And there are three problems with this approach so far, and this is what I want to work on. I want to change a little bit. First of all, if you want to implement these algorithms, these quantum algorithms on the hardware, this hardware is noisy. We have this noisy regime at the moment, and so we need to develop new quantum algorithms that deal with this noise. A second problem is that we in theory have always been thinking about worst case algorithms now, and I will say a little bit about that if I'm allowed. Algorithms that have a sort of a guaranteed performance in the worst case, but generally we are not interested in that. We really want to solve a particular instance, and we want to solve that quickly, and we don't care if the algorithm is slow on some other instance that we really don't want to know the answer to. So this leads to the notion of quantum heuristics, which I think is very intriguing and needs to be examined closer and developed closer. And then third, I will not really talk about that, but that is, we have been thinking in theory mostly about asymptotic analysis. And that means that you really get to have some opinion on how fast your algorithm is when the instances become really big. But again, we want to solve a problem for a specific instance of a specific size. And so we really need a new mindset here. And so our complexity theory that deals with this needs to be amended to work for finite inputs. And also this is extremely important in order to establish whether we have a supremacy or not. And so this is what I call quantum software 2.0. Is it okay if I continue a little bit, Yvonne?
Yes, go ahead, Hadi.
I take a few more minutes.
Yes.
Gilles won't be upset with me. So first problem of noisy qubits is that these qubits are noisy, and we are in this NISQ regime, as it's called, where we cannot error correct and do fault tolerance on our qubits. So really, as you use your qubits, they become unstable and more unstable. And if you wait too long, they're complete noise and completely useless. So you quickly have to do your computation. And that means that you can do really only a limited number of steps. So that means you can only run very short programs on your quantum computer. And moreover, the readout is probabilistic. So that means that you have to repeat your computation many, many times. And then take somehow an average outcome. And so it means that you have to run your computer often for short periods, and also you have to use a lot of classical computation before, in between, and after. And this is this hybrid computation. And we need to think a lot more about how to make optimal use of this paradigm. A couple of algorithms already reflect this, like the famous QAOA algorithms or the variational quantum eigensolvers. What we are at the moment at QSOF thinking about is how can shallow circuits help, where you really have short quantum parallel time and see if you can make somehow good use of that. And actually, it's kind of intriguing that Shor's algorithm, this famous algorithm that breaks a lot of cryptography, actually can be cast as a shallow quantum circuit. So Shor's algorithm, in some sense, is closer by than some people think. And then another thing that you have to do here is really make optimal use of your quantum hardware by something that I call Hamiltonian programming. Instead of going to the standard gate model of quantum computing, you go a little bit below that and you address the quantum systems in their natural language, which is a Hamiltonian that governs that system. And it's not clear how well all this really works in the NISQ setting, and that's sort of the intriguing thing that I want to work on also within the Quantum Delta program. We really will need new ideas, techniques, and fine-tuning to make all of this work. Then a little bit about problem 2, and that is this worst case versus real case, and it's best seen by picture. Here you see the running times of, in yellow, the best quantum algorithm, and you see in orange the best classical algorithm. And for example, what you see here on instance number 2, you see that the running time of the quantum and the classical algorithm are the same, which by traditional analysis would yield to the outcome that there is no advantage to be gotten here for this problem. However, you clearly see that there is an advantage here on instance 3, 4, and 5, and even on 1. So there certainly is an advantage, but we're not looking at it from the right perspective. And what I want to look at it is in a heuristic sense. So you try to design not the best algorithm that sort of has the best overall guarantee, but that has a good guarantee on instances that you care about. For example, suppose that we really care about instance 4 and 5, then this green algorithm, which I call a quantum heuristic algorithm, is performing really badly on instance 2 and 1, and on instance 3 it's doing as good as the previous one, but it's really doing much better on instance 4 and 5. And if you are interested in 4 and 5, this is the algorithm that you want, but it requires a completely different mindset than before. So quantum heuristics are a nice idea, but they're a little bit hard to analyze because we don't have a quantum computer to try them out on. And so we need a theory to reason about this. And this is also one of the things I would like to do. We do have a couple of examples where we do know that sort of this heuristic approach works, namely when you can actually use a classical heuristic and quantize that and make it a little bit faster. So that has been done. And there also are examples, for example, in the pattern matching setting due to Montanaro, where he showed that there is on average an advantage to be gotten there, actually exponential. So now we almost reached the end of my talk. So quantum software 2.0 is what I call it, tries to combine these things. It designs algorithms that deal in this NISQ setting. So it generalized and improved this QAOA and VQE algorithms, develop this hybrid algorithms, so you have really short running times, so you can make good use of your qubits. And this also means that you have to develop what we call shallow quantum circuits to do so. And then the second ingredient is this quantum heuristic algorithms, where you really want to optimize your algorithm for real world instances and sizes also. Well, in order to know that, you have to know what are the real world instances. And in order to know that, you have to talk to the customer, like the ABN AMRO Bank or Bosch or Toyota. And we have to develop tools to analyze these. And of course, all of this will be a mix of the two. And then I'm ending my talk with sort of a more general picture of how I see this all ending up in the quantum delta and how QSoft and Quantum Amsterdam add in. And that is through this hardware cycle and industry cycle and the feedback loops. And here on the left-hand side, you see the hardware cycle where you co-develop quantum algorithms and protocols together with the people who actually make the hardware, who make the quantum bits and the quantum networks. And there is really a dialogue going on at the moment, and this needs to be much more than it is currently, where the protocols that you develop on the blackboard get implemented on the hardware, but then it turns out the hardware doesn't really do what it's supposed to do, or rather what you thought it would do. And that means that you have to change your protocol so that it actually does fit on the hardware. And also you can tell the hardware people, look, it's unpleasant that you cannot do that, but maybe if you could make it so that it is changed a little bit, then that would help a lot. And so the new protocols and the new hardware are developed hand in hand. And then here on the right-hand side, you also see something called what I call the industry cycle, where on the one hand, you have people from academia who know a lot about quantum computing and the potential there, but don't know what industry or society wants. And on the other hand, the industry people know what they want, but they don't know what quantum computing is. And also here, a co-development cycle has to start. And all of this needs to be all chained together. And I see the whole quantum delta, at least for this part, doing that. And for example, this hybrid algorithms that I talked about, that is something that comes out of this hardware cycle. And this quantum heuristic demand is something that really comes out of this industry cycle. And I expect new things to come out of these cycles and lead us forward. Okay, so then ending with a warning, and that is that we all have to be quite careful because the field at the moment is overhyped with unrealistic claims. You hear a lot of it will very soon change the way we do computing, and it then is quantum computing, or it is a disruptive technology that is pervasive to everything, or quantum computing is the solution for big data bottlenecks or for anything else that there is a bottleneck. And of course, this is not at all true. And we have to be very careful because the truth really is that quantum computing is still in its very early stages. And perhaps it's comparable to the 40s and the 50s of classical computing. And we will probably not have a useful quantum computer in the next 5 to 10 years. We will have some small models that we can play with and that we can use to get an idea on what we do. But certainly, we have to be very careful here. The field at the moment is still very much in an exploring and academic mode. Nevertheless, it is extremely interesting and it has potential, but let's all please be a little bit realistic and not overhype everything. That's where I want to stop. I see a lot of...
Yes, thank you, Harry. Can you stop sharing your screen so we can see you full screen? Yes, thank you for your great presentation, sorry. Lots of things you can work on for the coming years within QSoft, Quantum Amsterdam, and the Delta.
Yes, I won't be bored.
No, the amount of algorithms can be endless, but you need input from the business, right? For the applications and
yes,
to know what you are looking for.
Yes, input in many ways.
Yeah, but there's a question from the audience and a comment. Thanks for the talk, Harry. Aiming for average case speedups. How do you deal with the fact that many hard problems are much easier in the average case classically?
Well, I mean, that's the whole point, right? So that gives also hope that they can be even easier for the quantum in the quantum setting. Moreover, there might be problems out there that are hard also on average classically, but in the quantum scenario, they are not hard on average anymore. So precisely the fact that this happens classically gives me hope that it will also happen quantumly compared to classically. So that's not something I want to deal with. That's something I want to exploit and explore.
Yeah, yeah. And then there's another question. What would be your super yacht, I guess, vision idea to speed up the queues of deliverables in the Netherlands?
I didn't catch the first word that you said.
Yeah, so what would be your, it says the super yacht, but I guess the person means idea, vision, or to speed up the queues of deliverables in the Netherlands.
Well, I guess a lot of coffee can help with that. I mean, this whole program, right, is trying to do that, and
Yeah.
I mean, this the putting manpower to this and smart people, setting them onto this and ask the right questions.
Yeah, exactly.
That will move that forward, and I guess cooperation with industry.
Yeah, so do you think that in 7 years, when the NACT is finished and all the money's gone, maybe not, that you have found new applications for business and that are already, if you have found.
Yes. Well, I mean, I certainly hope so. I can't guarantee, but I certainly hope that we will have made quite some big progress. I really hope we have some bigger systems that we can run our algorithms on by then. And for example, these areas where I talked about, where we talked about these chemistry applications and material design, those are the ones that could be already run at that time, hopefully. So that's what we anticipate, and so. I would say yes. I mean, there's going to be progress. Certainly, if so much effort is being put into this, there will be progress.
Yes, great.
Absolutely.
Yeah, so, well, we have time for you still to answer some questions from the audience after Gilles gave his presentation. But then for now, for the companies, for the people who are watching and working at a company who might want to do something with quantum technology, what would be your call to action for them? Like, do you want to work together with them?
Yeah, let's talk. Let's talk.
Yeah.
And,
contact you to make more algorithms.
And there are not a lot of people that you can talk to, and not only to me, but you can also talk to Gilles, for example. Actually, yes. After this meeting, I have to rush Gilles to a meeting about Canadian and Dutch cooperation.
Okay. Well, then I give the floor. Thank you, Harry, again. Yeah. We'll see you back later. I give the floor to Dimitri.
Yes, thank you, Yvonne. So last but not least, cliche it is, I know, but it's one of the B's in BB84. And if you don't know BB84, what are you doing here? No, seriously, but all the way from Canada, Professor Gilles Bessard, and I'm very proud that he is able to join us. So Gilles, thank you very much for joining us, and take us away. The floor is yours, and I'm very excited to see what you're about to present.
Well, thank you very much, all of you. Thank you, Harry, for the inspiring talk, and for taking so much time at that I will not. Nobody will notice that I didn't prepare anything because I don't have time anymore to speak. So sorry. Let's try to be serious, as you will see. I can sometimes. All right. I don't know what's going on. Ah, no. Sorry about that.
I think you still have to click the application that you want to.
No, that's not a problem. When I plugged in my iPad about 15 minutes ago, it told me that I needed a software update. So once in a while this happens, and I loaded it, but it doesn't work. So I will have to, instead, I had a backup plan. So that's good. Don't worry.
Ah,
There we go.
Here we
Great.
go. Here we go. Here we go. Here we go. All right.
perfect.
Very good. So I was asked to tell you what I would do with 615 million euros, and Harry started his talk saying that of course we could buy big cars and boats, but let's not bore you with this. And he went directly into something more serious. Harry, I'm ashamed of you. You're a Dutch. What you should have said is you would buy a very expensive bike. And I scored the internet on search of the perfect bike for this application. I think this one is really, really looks really good. I'm not sure I would want to ride it actually, but it's a piece of art. Now this bike was claimed to be the most expensive in the world at $70,000, and with the current exchange rate, you could buy about 10,000 of those with the money you have. However, this is of course not true. This is very far from the most expensive bike you can buy. This one, look at this beauty. It's gold plated, 24 karat gold, beautiful gears. This bicycle sells for about €250,000, and it doesn't even have pedals for that price. Anyways, so with a quick calculation shows that you could buy 2,500 of these. And this is nice because the announcement says that you expect to train 2,000 people. So you could buy one of these for each person, and there will be 500 left over for me. But so problem solved, you know what to do with the money, and then I can go. Not quite, there's a very bad news. It's sold out. So we have to find something else. How about this one? Well, the one before was 24 karat gold plated. This one is solid gold, which sounds fairly ridiculous. And it sells for $1 million. Expensive bike on the market, and it's not sold out. Sold out. You give one to each of these 2,000 people, and you ask them to carry qubits around with the bikes. All right, let's try to be more serious. Of course, you could buy a satellite. I'm not sure if you have enough money for that. This is the Messius Chinese satellite. This was discussed earlier today that satellites might not be the most cost-effective way to use such a small amount of money that you have. And it's probably the case that you investing in satellites at the moment may not be the best strategy for the Netherlands. In particular, because your territory is relatively small, and you can cover it with ground lines like fiber optics. So there are so many avenues for research in quantum everything. In particular, and also research and development. Of course, I'm on the research side, but I do not dismiss the importance of development. And some of that money should be used for developing real products, I suppose. But then we concentrate on research because that's really what I know. And then there are many areas, many directions in which you can do research on quantum stuff. Metrology was not even mentioned today, I think, and I'm not going to say anything more because I don't know anything about it, but I know that it's a buzzword. Quantum sensing, on the other hand, was heavily discussed in one of the talks this morning. So where we've learned that you could replace pendulums by atoms and save your neck by not having the king be late to his appointment with the queen. Quantum foundations. is the area which is closest to my heart, where we try to understand what's going on, to understand how this is all possible and what is possible, and how quantum theory differs radically from classical theory. And in quantum foundations, the Netherlands has done very important work. In particular, in 2015, if I remember well, for the first time an experiment was performed to test Bell inequalities violations without falling prey to either the location loophole or the detection loophole. Sorry for the jargon if you don't know what I'm talking about, but this was a very, very important experiment performed in Delft by Henson on the left and Hansen on the right, not to be confused, and a bunch of people in between. So quantum foundations is where I would personally put most of my money, because I think that's fascinating, even though it doesn't have an immediate application. But I think the main message that I always want to carry in any talk of this sort is the importance of basic curiosity-driven research, in which if you only care about short-term applications, you will not get very far. When Einstein and all the giants of the early 20th century, when they developed relativity and quantum theory, they had no idea that this would ever be useful for any application. They were just doing that for the sake of understanding nature. Again, what we call basic research, curiosity-driven research. And quantum foundations is in that line of thought, that we just want to understand what's going on. And who knows if and when it would have applications that would change our lives. Again, the early development of quantum theory was pure research, and today our entire society depends on what these people discovered, having no idea it would ever be useful for anything other than our knowledge. And then, of course, we want to build quantum computers, in particular for simulation, not only, but quantum simulation is in earlier reach than what we call a universal quantum computer that would be able to perform arbitrary quantum algorithms like Shor's factoring algorithm. And we had a talk that mentioned quantum simulations. So this is definitely part of the plans that you have in the relatively short term in the quantum delta. Foundations, computers, this is in particular done really, really well at QTech in Delft. So they are at the forefront of world research on these issues. But you should not confuse QTech with QTech. You might have never heard of the second QTech, which is not a second QTech. This stands for quantum technology. Quality technology, if I remember well. And it was founded in 1989. And I don't know why the Delft QTech was not sued by them when they chose the same name. But, well, these things happen. Also closest to my heart is quantum communication and all of its applications. I will say a bit about it in a minute. But quantum communication, I mean how to communicate quantum information for various purposes, from place to place, maybe a short distance or bigger distance or really big distance. But all of that, all of these things are essentially pointless if you don't know how to use them. And in order to make good use of all of these technologies, and particularly quantum computers, you need quantum software. And without quantum software, without what QSoft is doing, this is just building toys that you will not know how to use or what to do with. So in my opinion, and not only because Henry is listening, the development of quantum software is the most important aspect of this entire industry. People did not understand this in the early days of classical computing. In the 1960s, for instance, you would pay a lot of money to buy an IBM 360 computer. And it would come with almost no software, some, yes, but not so much. But software was free. When you bought a computer, of course it came with all of its software because people put all the money on the hardware. And then Microsoft came about, and other people realized the importance of software, classical software, which became a bigger industry, much bigger industry than a quantum, sorry, than the classical hardware industry. And we should not repeat this mistake in the quantum world. We understood from the classical experience that designing software is far more important than building the machines on which the software will run. I'm not saying that the latter is not important, of course, but they are both important. But without software, there's nothing to do with the hardware. Of course, you might say the other way around as well. But that's not true because you can still think about software, even if there's no hardware to run it on. Like Turing, when Turing designed a Turing machine, there was no computer to run his ideas. Still, Turing invented such a beautiful mathematical theory. And who knows if computers would ever exist in the 1930s when Turing developed his groundbreaking theoretical classical software, ClassSoft. Could have been a company. All right. Now, let me say a bit about communication. Quantum communication, how do you do that? Well, you could use optical fiber. First of all, whereas computing is better done with qubits that can stay in place, for instance, trapped ions or superconducting qubits on wafers and stuff like that, communication is better done with photons, with light. And light travels well in optical fiber. Or you could also do communication in free space. This has been done over significant distances as well. The advantage of free space is that it's less disturbing in the sense that optical fiber will lose photons on the way, and it decays exponentially with the distance. The advantage of fiber, on the other hand, is that it can go from between 2 points that are not in line of sight, which free space needs. You can also use satellites, which is by definition a form of free space, and the longest distance of quantum communication so far has been done with the Messier satellite over about 1,500 kilometers between ground and the satellite, and then the satellite can relay information from one place to another on Earth, so that a communication was established between Beijing and Vienna, I think 6,700 kilometers apart. You can also use quantum teleportation to move quantum information around, and I don't have time to explain that. But to do that, you need to establish an entanglement between the two locations that need to communicate. And it might seem at first that establishing entanglement is not easier than just sending the quantum information directly. But this is not true, because quantum entanglement can be swapped from place to place and then can be distilled. So you can create entanglement between two places too far away for a direct optical fiber link by creating entanglement from place to place. And then by entanglement swapping, if you have entanglement between these 2 points and those 2 points, you can make it between those two if the guy in between does something. And then you can do that up a binary tree, and in the end have arbitrarily or just very far apart points sharing entanglement from this process of entanglement swapping. And then the entanglement you get might not be very good. You need to distill it. And entanglement distillation will in the end get you really, really good entanglement between arbitrarily 4 points without need for a satellite. This is still a bit of science fiction because you also need very good quantum memory to do that. But it's definitely something that is, if I were an experimentalist, which I'm not, and if I had lots of money, I would invest some of it certainly in designing a long distance quantum entanglement link for the purpose of teleportation obtained by swapping and distillation. Now, that was why would you want quantum communication? Of course, for quantum cryptography that was mentioned before, Harry said probably Gilles will say a little bit about that. I don't really have time, but all I want to say is that quantum cryptography makes it possible in theory and to some extent in practice to establish a absolutely secure link between 2 points, which is with no need for unproved assumptions other than quantum theory is correct, which is an assumption, I must admit. But compared to the current infrastructure on the internet, which relies on unproved assumption on the difficulty of solving some problems, some of which we know how to solve with quantum computers if we had the quantum computers big enough to do that. So the current infrastructure is doomed because quantum computers will be able to break the communications that are currently sent on the internet and that have been using the techniques used for essentially since the internet was so-called secured. And this is really terrible because not only will communications become vulnerable once the quantum computer becomes available, but all the past communications also, because nothing prevents someone from taking down all the encrypted information that goes on the internet, unable to decipher it because that guy doesn't have a quantum computer yet, store them, and when a quantum computer comes about, can take all of this out and of storage and decrypt it, so that everything that's been so-called secure sent on the internet since its inception will become an open book when a quantum computer becomes available, except for a few months of a trial of other techniques by Google Chrome at some point. But essentially, everything that's been sent on the internet will become an open book. It's not even useful to attempt protecting the past. You can only try to save the future. And to save the future, you can either do that with post-quantum, so-called post-quantum techniques, which are purely classical, and which may, but we don't have to prove it, may be secure against quantum computers, or you can use quantum cryptography, or even better, use both. These two techniques can work hand in hand very well together. And if you want to use quantum cryptography, the problem is that you need, if you want to do that at long distance, then you need to be able to communicate quantum information over a long distance. You can do that with satellites. You can do that today. You can do that with satellite. Tomorrow, you can do that with entanglement swapping and purification and distillation, as I said before. But in the meantime, you can also do that with trusted relays. A trusted relay is if you want to communicate between 2 points which are too far apart for a single fiber optics to carry the information, then you put some relays in between. The information is encrypted at a starting point, sent to the first relay who decrypts it, gets it in the clear, then re-encrypts and sends the next relay, and all the way down to the recipient. So we call them trusted relays because these relays will know the information that we're supposed to protect. And this is what China has implemented over 2,000 kilometers with 32 relays between Beijing and Shanghai. And this is fantastic. China is very much ahead of the rest of the world in terms of quantum cryptography, both because of what they call this backbone that links Beijing and Shanghai, and also their satellite Messius that is also used for quantum key distribution. An untrusted relay is one that's what I talked about before. An untrusted relay would be able to establish entanglement over longer distances by entanglement swapping and entanglement distillation. So with an untrusted relay, you need the relay to distribute the entanglement, which can then be used for teleportation over arbitrary distances, but you don't need to trust the relay. If the relay misbehaves, then you will just fail, but you will know you failed. The relay cannot get access to the information that's supposed to be secret. So that's a big difference between trusted and untrusted relays for quantum cryptography. Quantum cloud computing is one application that I think is really interesting. The idea is that in the short term, well, in the short term, there's no quantum computer, at least we can hope so. In the medium term, there will be a few quantum computers, but not everybody will have one in their living room. So people who need quantum computing access will need to delegate to a big center that has its quantum computer, and very much like the cloud as we know it today in the classical world, but there will be a quantum cloud, and the quantum cloud will be used to compute on quantum computers remotely. But do you trust the cloud? You shouldn't, probably. Do you trust the classical cloud? To some extent, yes, I suppose, because it's so useful, so convenient, but you should not trust it blindly. So if you want to secure a quantum cloud for computing purposes, you need all sorts of cryptographic techniques that are being developed and that are really, really interesting, in particular by Anne Broadbent at the University of Ottawa, but many other people work on securing a quantum cloud. And the quantum internet, well, the quantum internet, let me just say a few more words about the quantum internet. This is a vision, it's an artist's vision of linking Europe in a quantum internet. I believe this is stolen from QTech, this slide, whatever. It's just very beautiful artist's vision when hubs are linked by this quantum internet, but also in each hub, there's a local area network. So in the end, you can communicate quantumly, which is not a word, between any point in any hub to any point in the other hub. And this is still for the future. But you know, in the 1960s or even 70s, if you told people that in order to communicate, to make a long distance call between America and Europe, you would go through satellites when everybody used the sub-oceanic cable, you would have been thought to be crazy. But of course, now that's how it's done. So you never know what's going to happen, and the future is hard to predict. And it is reasonable to hope that the global quantum internet will exist in some future. But in the shorter term, this is another slide I took from the earlier talks today. If you want to, the Netherlands has the potential to be the first country to be linked, thoroughly linked by a quantum internet. And you owe this to two things. One is that now you've got lots of money to do that. And the other reason is that it's relatively small in terms of area. You know, there are about twice as many people in Canada compared to the Netherlands, and the area is about of Canada is about 235 times bigger. So it's be much more difficult for Canada or China, no matter how much money you have, to link the whole country with the quantum internet. But you have a chance, and some of it is done already. So this is really, really exciting, and I think that it should be a priority, that you could be first in the world to really link the country with a quantum internet. But to do that, let me just repeat, none of that is possible without quantum software. So QSoft will rule the Netherlands, but they cannot do it alone either. And all the other players are very, very important for this quantum infrastructure and ecosystem to become live. Let me just finish to tell you that Canada also announced a quantum initiative. So there's a national quantum strategy that was announced just a few weeks ago in their last federal budget, and not nearly as much money as you have. Well, at least certainly not per capita, but still, there's hope that we will also be able to go forward in Canada and work together. So let me, as my last slide, this is taken from the Botanical Garden in Montreal, just to show you that there's a piece of Holland in Montreal, even when Harry is not here. And And I'll stop on that. So, oh, well, I'm just very nostalgic about my last long, several months stay in Amsterdam in about two years ago, in 2019. I spent about 3 months in Amsterdam, and this was a picture taken from my living room window, and I'm looking forward to being back there. Thank you.
Okay, thank you, Jill. Can you stop sharing your screen so we can all see one another some larger again?
Well, I'm trying, but my oh, there it is. No, there it is.
It's always
I know. I had lost the cursor, but I found it again.
But I think we're all going to look for those bikes and see if we can buy them, right? And
Yeah.
and we can make some progress there. It's interesting, you know. And talking about it's about the whole spectrum of this quantum development, right? You're talking about the foundations, and you're talking about, you know, it's about the software. You have the hardware, the software, but the software needs applications, and the applications you have the end users. So it's about everything. So this is a big thing, I think. If you talk about, okay, what do we need? What players do we need? This is too big just for QSOC. This is too big just for QTech. This might be even too big just for the Netherlands. So I think in general, it's about, you know, cooperation. Because,
absolutely.
Because I'm still wondering, you know, and I think Ronald Hansen described it as a black box in terms of, okay, explaining entanglement.
Why?
Because he said, well, we don't know why this is happening actually.
Well, I know.
You know. Well, if you tell me that in 2 minutes, I'll be interested. So explain quantum entanglement, please.
Well, what I mean by I know is I know how it's possible. I know it works in the real world, as opposed to just scratching our heads and saying it's magic. And it's possible to explain entanglement and everything that the entanglement predicts, and that we actually verifying experiments. You can explain all of that in a theory that is purely local. So it is possible to give a quantum state, or to define the state of every part of the universe in a local way. And whenever you act on it somewhere, there's no action whatsoever anywhere else. It's purely local. And yet all the predictions of quantum theory are valid in that explanation. So all this nonsense about quantum non-locality is, well, nonsense. There's no need to involve non-locality to explain any of that magic. And it's not magic because it can be explained. But no, I cannot explain in 2 minutes how this is done. This was first discovered by David Deutsch, the father essentially of quantum computing, together with Richard Feynman. David Deutsch and Patrick Hayden in 1999 discovered how to do that. And it was rediscovered by my then student a few years ago, Paul Raymond Robichaud, who generalized it to arbitrary theories. Any theory in which there is no observable action at a distance, such as quantum theory, which we call any non-signaling theory, can always be explained in local realistic fashion. But for that, invite me again to give a talk on this.
I think I need a couple of months to grasp the surface out of that, if I can deal with that. So hopefully when you're next time you're in Amsterdam, we can have a chat on that. And maybe we need a couple of bottles of whiskey along with that to fully understand it.
Good fuel.
Looking at the time, Yvonne, do we have some questions from the audience for these panelists?
We have some questions. There's a question from Frederik Kerling. Which more exotic quantum effects do you hope become everyday life accessible with the advance of the technology? An example, Wigner's friend game. Yeah.
Well, how about quantum teleportation for humans?
I wouldn't go in, Jill. But you can be my guest.
Oh yeah, good. Well,
Yeah,
that's
who
fine
wants to
because
try?
well, I would probably be more interested in going back to Amsterdam than you to Montreal. So it's
No,
right direct.
but I'd rather fly, not take the
Oh,
teleportation.
really?
Yes.
That's so slow.
But what happened to your copy here?
But it's destroyed, of course.
Well, good luck.
No, the thing that the only thing which is really sort of worrying is that if you know anything about quantum teleportation, the original has to be destroyed by definition. It's not a choice. It's part of the process. So it's not that once the copy is over there, then you push a button and shred the original. It has to be destroyed in the process of sending it to destination. But then at that moment, if you will allow me to pretend I believe in unlocality for a minute, because it's easier to explain in those words, even though it's nonsense. But at the moment that I am destroyed here, in fact, nothing exists at destination. It will only appear at destination once a classical signal at the speed of light is sent from sending to receiving apparatus. In the meantime, while this classical information is on its way, I'm nowhere. I'm destroyed from the original place, and I'm not in any way, I'm not at all at destination. So
And you hope this becomes part of our everyday life?
well, I think it would be really nice. Look. Asher Paris, who was one of the 6 inventors of teleportation, Asher Paris was he left us about 20 years ago, unfortunately, but he was a very devout atheist, as he described himself. And once a reporter asked him, if you were to teleport a person, would only the body be teleported or the soul as well? And his answer is beautiful for an atheist. He said, no, only the soul is teleported. Which is true, because if you know again about quantum teleportation, all the material, all the actual physical material to recreate yourself at destination must be there already. What is teleported is the soul. Now, all this being said, this is very unlikely to ever happen, teleportation of people. And so I was somewhat joking, but yes, if it were possible, yes, I would use it, certainly.
So then maybe I can continue now with another question from the audience to Gilles about foundations. Do you think we may find new foundational breakthroughs within the current theory of quantum, or do we need a whole new theory?
Well, that's a good question. In the history of science, real progress have always occurred by what so-called catastrophes. It's when we think that we understand everything, and then an experiment shows us that something is wrong with our understanding. And sometimes it all goes down crumbling and we have to start all over again. That's when real progress happens. And this happened, it's really amazing. It happened twice almost simultaneously in the early 20th century. In the late 19th century, we thought that this is it. Physics is finished. There were just a few clouds in our understanding, and those few clouds gave rise to quantum theory and relativity in the early 20th century. 2 catastrophes. Well, we knew the clouds. We knew that the few experiments could not be explained, but we thought it would be easy to solve. It was, in the end, solvable, but by really scratching everything and starting afresh. I think it would be very, very exciting if this happened with quantum theory. If an experiment would show us that we've understood nothing and it's time to start over again. Now that would not be I mean, I'm really talking about complete upheaval. It could also happen that quantum theory is mostly right, but it needs a few fixings, as people thought of Newtonian mechanics in the late 19th century. that would be much less exciting.
Yeah. Let's take it step by step and see what happens.
Yeah, that's right.
There's another question for Harry. We are already a bit over time, and there is a Wonder.me session, but I'm looking at Harry and Gilles, and we can also leave it at this. We do some more questions, and then the audience can ask them now. I'm not sure if you have enough time left.
Sure.
Sure. Okay. So a question to Harry about overhyping. What do you think of claims of some big companies, and then somebody added to it, companies like IBM, Honeywell claim to have 1,000 qubits by 2024. How realistic do you think these claims are?
Well, I can't answer because I'm not working for these companies, so I don't know the ins and outs. But
I guess they want to pick your brain.
usually, I mean, like company like IBM is kind of reasonably trustworthy. If they, and I've seen that on their roadmap that they have like 1,000 qubits in the 2024 or maybe within the first 5 years or so, then I would believe them, and I hope it's going to happen. But that 1,000 qubits still does not make it that you can solve all the problems in the world exponentially faster. Right?
And is it 1,000 noisy qubits?
It will be noisy qubits. So in this first regime that I talked about, this NISQ regime. So that seems it's great if that happens. It would be it's progress, but and it's not unrealistic, I would say, but. That's not the hype I meant. I meant more the hype saying that this is going to change everything, and in a few years we will have a quantum computer that will solve all your problems that you have now in computation.
Yeah. So you said approximately.
Sorry to interrupt, Harry, but it will change everything when people start teleporting themselves, isn't right?
Yes, they'll be dead. I mean.
There's another question, Harry.
Yes.
Earlier question during your presentation. Is there also a focus on the NIST PQC contest in a national agenda of quantum technology?
So what I can say is within the national agenda, within the quantum delta, there was this, I called it the blue center ball, which this action line 1, I think it's called, which is for breakthroughs and fundamental research. And within that, there is fundamental research for also post-quantum cryptography. So in that sense, there is attention for post-quantum cryptography, and that of course ties into this NIST competition. Yes. But it's not the case that the quantum agenda is directly has direct connection with this NIST competition. But people that work here do.
Yeah. Right. Well, I guess
so we have a question to Gilles. Maybe an interesting question, though. It's about the multiverse theory is able to explain entanglement. How likely is it to be right?
There is no possibility it's not right. No other theory. Well, assuming that quantum theory is not completely wrong, no other interpretation makes any sense whatsoever. So by elimination, the only thing that makes sense is the many-world theory, and therefore it's right. However, the many-world theory taken at face value as it was developed by Everett in the 1950s or 60s, I forget, was meant to solve the so-called measurement problem, not the locality problem. So if you think of many-world theory as whenever some quantum event happens here with two possible outcomes, make it simple, the whole universe splits. This is highly non-local. So what we need is what my student developed, called what he called parallel lives. So Paul Raymond Robichaud parallel lives, in which when a quantum event occurs somewhere, then there's a local split. When you think you saw one outcome, in fact you saw both outcomes in two parallel lives, but it's a local event. And this local splitting will ripple through space as time goes, but not faster than light. So in my opinion, I have not seen any theory that makes any sense other than this one. And therefore, It doesn't mean it's right, but unless someone shows me something else, then it will be my best bet. Let's put it this way.
Okay, thank you. How are we on time, Yvonne? Are we?
Yes. I think this is it. We are over time already, but it was great to have this Q&A at the end. Yeah, let's leave it here.
Mhm.
The two men in QSoft t-shirts. Thank you, Harry and Gilles, for your inspiring presentations, and
Thank you.
I think we can look forward to an exciting time. And I hope the audience at home now and the companies who are looking and the scientists have more insight in what quantum delta NL is doing. And even in Canada, there's a boost for quantum technology. In the end, we should all work together, I guess.
Oh, yes. Oh,
And
yes.
yeah, so if you at home are interested in more of these type of events that Quantum Amsterdam is organizing, then please subscribe to our newsletter. You can go to our website, contact our Quantum Innovation Officer, Koen Groenland. Yeah, and if you as a company want to get in touch or want to know more about the possibilities, we also organize workshops, a general awareness workshop, quantum computing. So, and this is really to get to know quantum. Yeah, and these meetups we do monthly. So this was a bigger one, but we also do smaller ones, so very low profile, and anyone can join, because we really need you at home to inspire the science as well. And there's another event that I want to mention specifically, which is an information session about the Quantum Delta NL National Agenda, which is on May 20, and you can also find it on quantumdelta.nl. All right, this is it.
No, what's happening? Sorry, I didn't get it. What happens on May 20?
There's an information session organized by Quantum Delta NL, and they're going to elaborate more on the national agenda. So yeah, if you are still eager to learn more, then you can go there. This is it. I leave you with this, and have a nice evening. And thanks again to all the speakers, also from the first part, and Dimitri and Koen and Martin backstage. All right.